Welcome to the Biochemistry Clinic. Today, I want us to look at fatty acid synthesis. So, we're just going to have an overview or an introduction to this metabolic pathway. First things first, this process occurs in the cytosol and, of course, when you're in a very well fed state. In order to build up fatty acids, we're going to need acetyl-CoA. This acetyl-CoA is not strange to you, especially that we have already covered aspects of carbohydrate metabolism. We know that from glycolysis we can produce pyruvate. Pyruvate can be decarboxylated to form acetyl-CoA in the mitochondria. So this same acetyl-CoA is what we are going to use in the cytosol to produce fatty acids. Now, acetyl-CoA is in the mitochondria, and fatty acid synthesis occurs in the cytosol. What are we going to do? So, this acetyl-CoA has to be transported to the cytosol via what we call a citrate shuttle. Why are we using the citrate shuttle? This is because acetyl-CoA on its own cannot cross the mitochondrial membrane to enter the cytosol. So, acetyl-CoA is converted to citrate, and then citrate is moved out of the mitochondria into the cytosol. And once in the cytosol, we know that citrate can be broken down by citrate lyase to recover our acetyl-CoA and also produce oxaloacetate. And for oxaloacetate, it can still find its way back into the mitochondria by being converted to malate, and it also uses the malate shuttle back into the mitochondria. But that's a story for another day. Today we focus on the acetyl-CoA that we have successively moved from the mitochondria into the cytosol. Now, what exactly is going to happen in the cytosol? In the cytosol, we are going to use a 2-carbon molecule, which is acetyl-CoA, to build a 16-carbon molecule, which is palmitic acid. And so you're going to require a series of reactions to actually convert a 2-carbon molecule into a 16-carbon molecule. The first and most important step is the conversion of acetyl-CoA to malonyl-CoA. This step commits acetyl-CoA to lipogenesis because once malonyl-CoA is formed, we know that the process of fatty acid synthesis is actually going to occur. Now, this must be remembered. And the enzyme that catalyzes this step is acetyl-CoA carboxylase. Why carboxylase? Because it actually adds a carbon atom to acetyl-CoA to produce malonyl-CoA, and this carbon atom is actually in form of carbon dioxide. So this is the rate limiting step, and this is the enzyme that catalyzes this very crucial step. And this is the step that we're going to exploit for most of the regulation of fatty acid synthesis. Now, elongation during fatty acid synthesis occurs on a complex known as the fatty acid synthase complex. This is a very, very interesting complex, as we're going to see in our next lecture. So for today, I'm just going to give you an overview of what actually happens on the fatty acid synthase complex, which has the cysteine component and the ACP component, where the primer acetyl-CoA and the malonyl-CoA attach respectively. So you're going to notice that in order to elongate the acetyl-CoA, you need a primer acetyl-CoA, which is going to sit, first of all, on the cysteine component, and then you're going to have a malonyl CoA, which will be on the ACP component of what? The fatty acid synthase. So that malonyl CoA can now be used to bring 2 carbon atoms at a time and add to the already existing primer of acetyl CoA in order to elongate the chain up to the time when we get our 16 carbon atoms. That's when the elongation process will be halted. Now, something that we just have to quickly look at before the next lecture is the reactions that actually occur. So I'm just going to give you a brief idea of what will be happening on this complex, the fatty acid synthase complex. So like I said, you have your primer acetyl CoA, which is attached to the cysteine component of the fatty acid synthase complex. And then you have your malonyl ACP, or the malonyl that is attached to the ACP component. These two are going to undergo a condensation reaction, which is a very critical reaction. This condensation reaction of acetyl enzyme and malonyl ACP will produce a ketone. And this condensation involves the removal of a carbon dioxide molecule, meaning that what we are forming is a 4-carbon molecule. Now, it is that 4-carbon molecule that is of utmost importance. It is very, very critical. So once acetyl CoA and malonyl CoA combine via the removal of a carbon dioxide molecule, we're going to form this ketone. Now, this ketone is the one that is going to undergo reduction. Then after reduction, you're going to have dehydration and another reduction step in order to produce butyryl ACP, which is a fatty acid that only has 4 carbon atoms. So once you produce your ketone in the first step of elongation, this molecule will undergo reduction to form an alcohol. The alcohol will undergo dehydration to form an alkene. The alkene will undergo reduction to form this fatty acid with 4 carbon atoms. The other thing that I want you to note from these reactions is that in step 2 and step 4, we're actually making use of NADPH, which is a reducing agent usually obtained from the pentose phosphate pathway, as we discussed. So NADPH in step 2 and NADPH in step 4. Very important for you to record. Now, what next after forming a 4-carbon fatty acid known as butyryl ACP? Now, this is where it gets interesting, as we're going to see in our next lecture, because this 4-carbon molecule is what will now sit in this position where you have the primer acetyl CoA in the first place. Now, as the 4-carbon butyryl CoA sits in this position, the malonyl CoA, which is the supplier of the 2 carbon atoms at a time, will again undergo what you call a condensation step, where malonyl CoA donates 2 carbon atoms to the butyryl ACP molecule, and another carbon dioxide molecule is produced. Now, when you add 2 carbon atoms to butyryl CoA, you're going to have a 6-carbon molecule. Now, that 6-carbon molecule will go through all these steps again, and again that 6-carbon molecule will be the one to sit in this place, and then you add. Malonyl CoA is continuously in supply to add the 2 carbon atoms at a time. So you have a 4-carbon atom fatty acid being produced in the first cycle. You add 2, you form 6. You go through this, you add 2, you form 8. You add 2, you form 10, until you have a molecule that has 16 carbon atoms. That is when this process is going to be halted. So that is just an overview of what fatty acid synthesis is all about. You're using acetyl-CoA, a 2-carbon molecule, to build a 16-carbon molecule, which is palmitic acid, through the help of malonyl-CoA, which acts as the donor of those 2 continuous carbon atoms that you are adding at a time. So please do not miss the next lecture, because we're going to look at the technical aspects of fatty acid synthesis. Thank you very much.